Dear students, welcome to my class on waves. Today in this video, I am going to explain you how transverse waves can be represented mathematically by considering the transverse waves along a stretched string. So what are transverse waves? Waves in which particle of the medium will oscillate in a direction perpendicular to the direction of propagation of the wave are known as transverse waves. So if you consider a stretched string, and if we give a small pluck at one point, the string will oscillate along this direction, then we can see that a wave will be propagating along a perpendicular direction. That is, a transverse wave is formed. Since this wave is propagating along a string which is one-dimensional, this wave can also be classified as a one-dimensional wave. That is, transverse vibrations along a stretched string can be considered as one-dimensional transverse waves. Now we are going to represent this mathematically using a second-order differential equation. For that, we will consider a stretched string which is having a length small l. And if we consider a small element dx which is having a small length of dx, we can consider 2 points in between. The distance will be equal to dx. Now x is the normal direction of the string and y is the position in which it will vibrate. So these two points are under consideration. So these 2 points are actually two nearby points. So since the string is stretched, the tension will be uniform throughout the string. We can represent tension along the string with capital T. And if the string is such tightly stretched, then two nearby points will be having their tensions directed oppositely. That means these 2 points will be having their tensions directed oppositely. You can see in this figure that at this point tension is directed along this direction, and at this point the tension is directed along this direction T. Then theta 1, here theta 1 is the angle which this tension makes, direction of tension makes with the horizontal, and at this point theta 2 is the angle which the tension makes with the horizontal. Now tension T, it's a vector, and we can resolve this vector into two components. One is the horizontal component and the other one is the vertical component. Horizontal component at this point will be equal to T cos theta 2, and the vertical component will be equal to T sin theta 2. This T sin theta 2 will be directed upwards, along this direction. At this point also, the tension can be resolved into two components. One is T cos theta 1 along the horizontal direction, and along the vertical direction the component of tension will be equal to T sin theta 1, which is directed downwards. So we are considering these 2 points having a small length of dx. From origin to this point the distance is x, and from origin to the second point the distance is x plus dx. That means the difference between these two, the difference in distance between these 2 points is small element dx. So x is the normal direction of the string and y is the vertical displacement of the string. Now we will see how we can derive a differential equation with this transverse vibrations along this stretched string. If you are considering the string which is stretched and the tension will be uniform throughout the string, and if you pluck at the center and let it free, it will vibrate along this direction. Then a wave will be propagating along a perpendicular direction. So we are considering the small length dx. So what will be the resultant vertical force? Resultant vertical force acting on the small element dx, that will be equal to T sin theta 2 minus T sin theta 1. This will be the resultant vertical force acting on the small element dx. Here we are not considering the horizontal component, we are only considering the vertical force, the resultant vertical force acting along the small element of the string which is having a length dx. Since here we know that theta 1 and theta 2 are very small, then sin theta 1 will be approximately equal to tan theta 1, and sin theta 2 will approximately be equal to tan theta 2. You know that tan theta is equal to sin theta by cos theta, and if theta is very small or tending to 0, cos theta will be equal to 1 and tan theta will be equal to sin theta itself. So the resultant equation becomes resultant vertical force F is equal to T tan theta 2 minus T tan theta 1, or taking T as a common factor, the resultant force is T into tan theta 2 minus tan theta 1. What is tan theta? Tan theta can be defined as a slope of the curve at a point. Slope of the curve at a point is defined as tan theta. Here the slope of the curve is dy by dx, y along the vertical direction and x along the horizontal direction. So here at the point where the distance is x, tan theta 1 will be equal to dy by dx at the point x. It is notated like this, dy by dx at the point x. Then tan theta 2 will be equal to dy by dx at the point x plus dx. So you can substitute this into this equation for force, that is resultant vertical force F is equal to T into, for tan theta 2 you can substitute dy by dx at x plus dx minus tan theta 2 is equal to dy by dx at x. So the resultant vertical force is T into dy by dx at x plus dx minus dy by dx at x. We can mark it as equation number 1. Now the string is having a length L, then let small m be the mass per unit length of the string. It is not the mass of the string, but it is the mass per unit length of the string, otherwise known as the linear density, mass per unit length. So what will be the mass of the small element having length dx? Yes, it will be equal to m into dx. So m dx represents the mass of the small element having length dx. So the transverse velocity of that small segment will be given as dy by dt. Velocity will be equal to, for that small element, dy by dt will represent the velocity, and also d square y by dt square represents acceleration. So what will be the force on a small element according to Newton's second law of motion? That will be equal to mass into acceleration. Here the mass is not equal to m but equal to m into dx. M into dx is the mass of the small element having length dx, where mass m is the mass per unit length. So this mass into acceleration, d square y by dt square represents the force acting on the element having length dx. So you can equate between these two. Equation 1, we can equate it with equation number 1, that is mass into acceleration. M dx into d square y by dt square will be equal to the resultant vertical force acting on the small element t into dy by dx at x plus dx minus dy by dx at x. So this will be, you can take m and dx to the other side, m to the denominator and dx also to the denominator, and writing it like this. T by m, the T is the tension, m is the linear density or mass per unit length. Then in the numerator we have dy by dx at x plus d by dx of dy by dx into dx minus dy by dx all divided by dx. This is of the form f of x plus dx is equal to fx plus d by dx of fx, d by dx of fx into dx minus f of x. So using this expression we can substitute here. Then d square y by dt square will be equal to t by m. And what does this term represent? This term represents the second derivative of y with respect to x. This term represents the second derivative of y with respect to x, that is d square y by dx square. So here the equation becomes d square y by dt square is equal to t by m into d square y by dx square. This is similar to our one-dimensional wave equation. Our one-dimensional wave equation is of the form, you remember the one-dimensional wave equation, that is of the form d square y by d square psi by dt square is equal to v square d square psi by dx square. This represents a one-dimensional wave equation which we have studied in our earlier classes. So comparing those two equations, d square y by dt square is equal to t by m into d square y by dx square, and d square psi by dt square is equal to v square into d square psi by dx square. We will get this v square term. which is equal to T by M, or V will be equal to root of T by M, where T is the tension and M is the mass per unit length or linear density of the string. So this V is the velocity of propagation of the wave. And now, since the string is oscillating, it will be having frequency of oscillation. If nu is the fundamental frequency of vibration, then this nu will be equal to nu in V. This V will be equal to nu into lambda, or velocity will be equal to frequency into lambda, or this nu will be equal to 1 by lambda into V, or nu is equal to 1 by lambda into root of T by M. Here we can substitute for V. V is equal to root of T by M. That is, frequency nu is equal to 1 by lambda into root of T by M. Now here, if you are considering waves along a stretched string, and if you consider one complete wave, it will be like this. The complete wave will be like this. Then each loop will be having its length which will be equal to half of this wavelength. That is, if this is one complete wave, then it consists of two loops. Then one loop will be equal to 1/2 of wavelength. That is, L will be equal to lambda by 2. Length of our string will be equal to half wavelength, where lambda is the wavelength of the wave. That is, L is equal to lambda by 2, or lambda will be equal to 2L. Then finally you can substitute in the equation for frequency. Fundamental frequency nu is equal to 1 by 2L root of T by M. Our frequency of vibration or frequency of the wave passing along the string, both will be equal. That frequency nu will be equal to 1 by 2L into root of T by M. So the frequency of the waves or frequency of vibration depends on three factors. One is the length of the string which is vibrating, then T, capital T, which is the tension along the string, and small m, which is the mass per unit length. Not the mass, it is the mass per unit length. So the fundamental frequency of vibration depends on three factors: length of the string, then tension along the string, and then the mass per unit length of the string. With this equation for frequency, we can state three laws of vibration. There are three laws of vibration which can be stated like this. That is, first law of vibration is, if you keep T and mass per unit length as a constant, that is, tension and mass per unit length, if they are kept as constant in the case of a transverse wave by moving along a string, the frequency of vibration or frequency of the wave mu will be directly proportional to 1 by L, or the frequency is inversely proportional to the length of the string. The frequency of vibration is inversely proportional to the length of the string. As the length of the string increases, frequency decreases. Frequency will decrease with the increase in length of the string. If you are keeping tension and linear density as constant, if both of them are constant, then nu will be inversely proportional to length. That is the first law of vibration. That is the first law of transverse vibration. Now we have the second law. Second law is second law can be considered if you keep L and M as constant. That is, if you keep the length of the string and linear density as constants, then frequency, fundamental frequency nu will be directly proportional to root of T, or it will be, frequency will be directly proportional to square root of tension. Frequency will be directly proportional to square root of tension if length and linear density are kept as constant. That is the second law of vibration. That is, it is directly proportional, or it increases with the frequency increases with the square root of tension. Then we have one more law of vibration. That law of vibration will be like, if you are keeping, now we have considered the relation between frequency and length, then frequency and tension. Similarly, you have a relation between frequency and mass. What will be that? Can you infer what will be the third law of vibration? Third law of vibration. For the third law of vibration, you have to keep tension and length as constant. If T and L are kept as constants, then nu will be directly proportional to 1 by root of m, or nu will be inversely proportional to root of m. That is, fundamental frequency of vibration nu will be inversely proportional to square root of the mass. That is the third law of vibration. So these are the 3 laws of vibration.